All right, I think we're going to go ahead and get started. My name is Ben Snively. I'm a Specialist Solutions Architect at AWS. I focus on the data and analytics services as well as the AI and ML services. In today's session, we're going to be covering big data best practices and how to structure the architecture when you're building big data and analytical systems. The way we're actually going to be stepping through this is we're going to be stepping through first framing analytical systems by some common challenges and constraints. How are customers facing these big data systems, and what are some common characteristics of those systems? We're going to step through a set of reference architectures, and doing so, we're going to map various tools, both AWS tools as well as open source tools, to see where they fit into those reference architectures. We have a couple demos throughout to show some real systems running. They're all live demos, it's not recorded, so we're going to switch to some demos throughout here, and then finish out with a couple customer references. I should let everyone know this is a 200-level session, meaning we're going to talk a lot about reference architectures. We're going to give a few demonstrations. We're not going to dive 400-level deep on any single service like Kinesis or EMR or Redshift. We have separate sessions for that, but this is meant to be an overview of the different types of architectures and where the services fit into those architectures. And as we get started here, it's really good to frame not every big data system is the same. So there's not a single one-size-fits-all for these analytical systems. What we find is there's really different types of systems. So some customers are looking at doing batch and interactive analytics with their data. Other customers are looking at being able to take real-time data feeds and being able to not only ingest that data and store it in a repository, but also be able to drive insights in real time and take actions on those insights. And then, of course, being able to take data, build models, power inferencing, and do machine learning with that data. So as we're stepping through these reference architectures, we're going to show architectures for stream processing, for data lakes and batch interaction, for machine learning. And I should note that you don't have to pick one of these. These aren't mutually exclusive. So you don't have to boil the ocean. You don't have to say, I want to do stream processing instead of batch or interactive processing. You could start small, architect it in a way to start building on top of those, and then incrementally add to the capability as you're building it. It's really good to be able to frame these services when it comes to how the delivery model is. So most people in the room are probably familiar with virtualized servers, EC2. So when customers are running things like Kafka, and we'll talk about what this is, on EC2, that's a virtualized service, meaning you as a customer would manage the Kafka and all the other components above the OS. We have services that fit into the managed category. So things like EMR, which is our Hadoop platform as a service. Things like RDS. These services, you don't necessarily have to manage the servers yourself. We'll do that on your behalf. So you can set up a Hadoop cluster, tell us you want it to be 10 nodes, scale to 100 nodes, scale back down to 50. And you can configure all this, but you as a customer are still thinking about servers. So you're still taking a look at what you need, setting up the auto-scaling policies and saying, I want this number of servers, here's how I want to scale it. When we look at serverless or clusterless, things like Lambda, Athena, Glue, these are services that really abstract out the servers away from you. We're going to give a couple demonstrations of things like Athena, where we're going to be performing SQL-based analytics on data. Even though we're going to be using SQL, we're not going to be actually storing the data in a relational database. So we're going to be querying the data under the covers that's using Presto, which is part of the big data ecosystem. And what you do is you just issue the query. You don't have to worry about if it took 10 servers, 100 servers, whatever it took to actually execute that query. So the servers are completely abstracted away. You just write the code, you write the analytic that matters. And this is important when you're looking at the different types of tools out there. So as we're looking at these architectures, we're going to be looking at open source products. We're going to be looking at partner products and AWS services and fitting them into these architectures. And as we're fitting them into the architectures, it's good to analyze, does it make sense to roll your own on EC2? Does it make sense to use a managed service or a serverless service? So as we're stepping through here, we're going to be looking at what are the various reference architectures, what are the tools that help me implement that reference architecture, how would I put together those tools. We're going to give a couple demonstrations later on towards the end of this. And really, why am I putting these tools together specifically? And before we dive into that, it's really good to set some tenets, set some principles as we're looking at these best practices and architectures. This first tenet isn't exclusive to big data analytics. It's really building loosely coupled or decoupled systems. What that really means here in the big data space is the way I analyze my data shouldn't be dependent on the way I collect my data. Meaning, I could change the way I collect my data, the tool, maybe it's streaming, maybe it's batch-oriented, but I want to decouple the way I collect my data, the way I store my data, the way I process and consume the data. And that really lets you future-proof, that lets you iterate, and build a system that lets you really migrate it over time. And we'll take a look at a couple of those examples. And if you have that loose coupling, another one of the tenets is being able to pick the right tool for the right job. So rather than trying to pick one tool that does absolutely everything, if you have streaming data and you need to do real-time analytics, maybe you'll use something like a Spark Streaming or a Kinesis Analytics or a Flink to be able to do that. If you really want to be able to do machine learning or deep learning, you're going to use different libraries like MXNet or TensorFlow or one of those tools to be able to do that. So the key is being able to architect it so that the data stays in one spot. You have a logical data model or a data set of that data and are able to use these various tools to be able to ingest and process that data. This isn't really an architectural tenet, but really lets you have speed and agility. But anytime you can leverage those managed services or serverless services, it really lets you focus on what matters. It lets you focus on the analytic, the transformation, the ETL, and rather than loading software and those other pieces. So this is a really good aspect. It's not really an architecture, so you could swap out, for example, a Kafka to a Kinesis data streams, depending on how you're architecting it. But it's a really good principle that we work with customers on. Event journaling, what this means is as you're collecting your data in these big data systems, it's really, really good best practice to not overwrite your data. So if you're getting data records and some of those data records are getting corrected, rather than replacing those records, keep appending to your data set. Keep adding to that data set. And what happens in these big data systems and why that is if you have large volumes of data and if there's ever an issue, an error in your ETL process, if there's an issue on somebody accidentally going in and deleting something or something like that, you always have your source of record in its original form you could go back to and be able to then analyze and process and then rehydrate or regenerate your data sets. And we'll look at how that looks when it comes to data lakes and S3. We have a couple other sessions dedicated to data lakes, so we're not going to spend a lot of time on that, but we'll give a few examples. Be cost conscious. Excuse me. A lot of times big data doesn't have to be big costs. If you architect it correctly, let's say you're building a Hadoop system, if you're decoupling compute and storage and scaling those independently, you could build a very, very cost-effective and performant system and keep that cost down. And lastly, adding machine learning. This is definitely a rapid trend we see. More and more customers, as they're collecting the data, wants to be able to leverage application-level services, platform services, these different services to be able to build their models. So as we're framing this, we're going to frame it around this simplified data processing pipeline. And this is definitely not necessarily every pipeline we see, but it's good to be able to set context around some logical constructs here. So if you take a look at this, we separate out into collecting. How am I going to capture and collect this information? And the key thing is, if I have different data sets, I may not want to collect the same type of data or different data sets the same way. So if I have GPS data or clickstream data, I might want to collect that very, very differently than if I'm collecting imagery or satellite data. So as we're stepping through these architectures, we'll categorize these services into what they're good at in these different phases, being able to collect, store, process, analyze, and consume the data. And you'll notice there's cycles here. It's not necessarily a waterfall. Oftentimes you collect and store the raw data. That raw data is oftentimes in the original form, so it might be CSV, JSON, whatever form it may be. Then you oftentimes really want to be able to take that data and create curated data sets, query optimized data sets to be able to very rapidly access that data. It could be through interactive queries, through machine learning, through your data warehousing. So this is a really iterative process once you collect the data, start getting it into a canonical or normalized form, and then ultimately consume it by different stakeholders. So as we're talking about this, oftentimes we talk about temperature, high velocity of your data, high velocity of your queries, high velocity of your analytics. And when we're stepping through this, we're going to be talking about the temperature across those spectrums. So let's go ahead and step through. I need to remember to stay behind here. So if you look at the collection phase, so oftentimes you have different data sources. So you might have records coming in from transactional databases. You might have a relational database. You might have a Mongo or a different type of NoSQL database. And these oftentimes are records coming in that you need to be able to analyze and process. And we could call those transactions. Similarly, you might have log data, application logs, media files, these large file objects that you need to be able to store, and then streaming data. And the reason we like to show this a lot of times is each of those collection methods, when we're helping customers architect their solution, oftentimes require a different way of collecting that data. So we're talking about things like how to do streaming analytics and collect streaming data versus how to collect data from a relational database as an example. And when you're looking at being able to store this data, if we take a look at storing the data, oftentimes transactional data goes into one form of a database. It might be a NoSQL database, it might be a relational database, and we'll step through some of the trade criteria of that. Media and log files, really the de facto standard there is really S3. If you're doing this on premises, that would be similar to doing something like HDFS with your Hadoop cluster, where you want a big file store or a big object store, a data lake, that sort of thing. And with stream storage, it's really data streams coming into some sort of stream storage. And really what that means is different sets of tools you could use. So the first one is Apache Kafka. This is an open source project, pretty well established. We have lots of customers going from hybrid solutions, hybrid architectures, or built these types of solutions on premises that are running Kafka today. And you can very easily bring that into AWS, run it on your EC2 instances, run it in a virtual hosting area to be able to bring that into AWS. You have Amazon Data Streams. So Data Streams is a little different, where Data Streams is really at the highest level. So when you define a data stream, what you define is a number of shards. Let's say you want to be able to process 1,000 records per second. That's a single shard. If you want to scale up to 100,000 records, you could very easily just change the shard numbers. You don't have to worry about, is it taking 10 servers, 100 servers, how many servers under the covers across all the different availability zones to make it highly available to be able to do that. You just configure, based on the sharding, how much capacity you want out of that pipe. And what we did is we actually released that first out of the Kinesis platform. And then we saw customers using that for a very, very common use case. What if I have streaming data, IoT sensors, GPS, clickstream, any of that streaming data sources? And really what I want to do is instead of doing real-time insights, I want to capture that data and do some sort of advanced processing or offline processing of that data. And that's where Kinesis Data Firehose comes in. What that allows you to do is configure an endpoint to be able to store the data. So you could configure things like S3 if you're populating a data lake. If you want to populate an ELK stack, you could configure Amazon Elasticsearch. You can configure these various destinations to be able to store the data as the data is flowing in. And that is actually priced a little bit differently than things like Kinesis Data Streams. So in data streams, you actually configure a number of shards. With Data Firehose, it's purely based on the amount of data that's sent through that pipe. So you don't have to pre-provision. There's some soft limits of records per second within your account, so always take a look at those soft limits. But you don't have to actually pre-provision for 5,000 records all the way down to 300 or whatever it may be. It's really billed per megabyte or per gigabyte sent through that pipe and then stored into your backend repository. So we have a few of these throughout this presentation. Don't worry, these are all going to be on SlideShare as well. But here's some of the trade criteria of what type of stream service to use. And one question I like to ask a lot of times when customers are looking at things like, for example, SQS versus Kinesis. SQS is a really, really great service. It allows you to have reliable queuing within AWS. But if you really need to be able to have a one-to-many fan-out, if you have streaming real-time data that needs to be able to process and reprocess later on, that's really where stream storage comes in, versus have one consumer take a message off the queue, have a visibility timeout, that sort of thing. So if we then shift over and look at object storage now, S3 is really the de facto standard method of storing objects or storing files out into the cloud here. And what it allows you to do is really build your data lake or build that object storage very, very robustly. And what I mean by that is you could very easily run lots of different analytics on S3. It's really natively supported by a wide number of tools, including the Hadoop ecosystem, including our service called EMR, our Hadoop platform, but also our partner products, Cloudera, MapR, Hornworks. They're all able to talk to S3 natively to be able to read and process that data. We're actually going to give a couple demonstrations here in a moment, processing data directly out of S3 through EMR, our managed Hadoop platform, using SageMaker Jupyter environment to be able to show a couple demonstrations. The other really powerful thing, and it's interesting, I came from an environment where before joining AWS about 4 years ago, I actually built a set of large Hadoop clusters on premises. And if you would have asked me before if you decoupled compute and storage, like back when Hadoop was coming out, people would look at you like you're crazy because that was the whole premise of MapReduce, right? You wanted to bring the compute to the storage and be able to process that. What we're really finding is both through this evolution of these types of analytics, things like Spark with the RDDs and the data frames, Presto, these different types of analytics, as well as how it's architected to be able to talk to S3, you could really very, very performantly decouple this compute to the storage and still run these Hadoop-based workloads really, really effectively. We have customers like FINRA running very large HBases purely backed by S3. So they're not using HDFS for their different log files and stuff like that for their HBase. They're talking directly to S3 for all those artifacts. So you could architect it so that it's very, very performant. We do have some edge cases working with customers where they want to cache that data, be able to store that data locally. S3 oftentimes still becomes the source of record, and we have services like S3 Disk Copy. It's a library you could run to create caches of that data on your cluster to be able to have, if you really do have the repetitive reading off of disk over and over again, maybe it's an old Pig or Hive job that is constantly running on that data set. With S3, you get a crazy amount of number nines, 11 nines of durability. I think that means that if you store 10,000 objects, you might on average lose one in every million years. Tremendous data reliability. I'd never achieved that when I was building on-premises Hadoop clusters. You also don't have to worry about data replication within the region. So if you're actually building these systems, a lot of times you have to worry about replicas or copies of the data within the region. With S3, you don't have to worry about that. That's all handled under the covers. That's one of the reasons you achieve that, or we achieve that durability number. It's very, very secure and low cost. So let's talk a little bit about data tiering. So when it comes to data tiering, we actually just announced, it doesn't have it on the slide, we actually just announced a new intelligence tiering. I don't know if you guys saw it today. So imagine there's a line on this slide that talks about that as well. But with data tiering, you could actually tier your S3 storage based on different classes. So the very frequent data that you're always accessing is usually in standard. You have infrequent access, you have Glacier. We have a report you could run called the S3 Analytics report that would tell you, which objects it recommends to be able to shift between the storage tiers. I should mention, we do have customers still leveraging things like HDFS. When you launch a EMR cluster, which is that Hadoop managed platform, or when you launch one of our partner products running Hadoop on AWS, there's still HDFS, there's still scratch space, there's still that location to be able to have, to be able to very rapidly read and write from. S3 just becomes that source of record that is always referred back to. So we've talked a little bit about streaming. We've talked about object storage. We're going to dive a little bit more into databases and then give a few demonstrations of these things here. So when it comes to databases, there's really a wide number of databases that are out there that you could use. The top two really are caching services. So Elasticache allows you to do Redis or Memcached. We have DAX, which is really a DynamoDB front end that has a write-through cache to be able to cache your DynamoDB. Neptune, one of my many favorite new services, to be able to have property graphs or RDF graphs and be able to do very, very rich graph queries against your data set. DynamoDB, which really allows you to store key values or JSON documents within it. And then RDS, both kind of vanilla RDS that lets you run a wide number of different engines as well as Aurora. And you might ask, which tool should I use? If I'm building a system, should I use a graph database, or should I use a document storage, or should I use a traditional RDBMS? And really what we find here is really choosing the best tool for the job. And the way we help customers choose that is through a set of questions. So if we take a look at some of the questions that we oftentimes ask customers, it really stems from things like, what is your data structure? Do I have a very fixed schema? Am I doing key value lookups? So if, a great example is if I'm storing tons of session data and I want to store that in a Dynamo or a key value store, it's very, very easy to be able to store that and retrieve it based on the key. Is it very, very relational data and I'm constantly traversing the graphs and doing different properties on that graph? So the data structure itself will help you very, very easily dictate kind of what the right tool for the right job is. But also the data access pattern. I have a lot of discussions with customers on, should I use Aurora or should I use Redshift? And really, the way the data gets ingested and the way you're using that data will help you answer that pretty quickly. If it's a very, very high throughput transactional data need, then Aurora is a great option. If you really need that analytical capability, you really need a OLAP rather than a transactional database, then that's where we see customers use Redshift. I'm going to put the clicker down. So here's one of my favorite tables that I promised you guys will have a ton of throughout the session here. So within here, I highlighted two different rows just to call out. So if you're looking at these different options, one of the key things is what's the use case? The use case, in my opinion, should really drive the major decision here. If it's log data, you notice we'll call out Elasticsearch. If it's OLTP, very transactional, something like Aurora. So the use case will really drive a lot of that, but also that shape of that data. What does that data look like that's needed to get stored? The other thing I should mention is a lot of these services either runs at the regional level or runs within your VPC. And when you're looking at architecting your solution, it's good to be able to look at these services and say, this service is really one that runs in my AZ, for example, or in my VPC, for example, RDS. RDS runs, you get an ENI, a network interface within your VPC. Versus something like a DynamoDB. DynamoDB operates at the regional level. You don't have to worry about replicating that across AZs. We do that for you. You can set up endpoints within your VPC. But as you're looking at these options, it's good to, as you're architecting out and looking at that diagram, which ones of the services run within the VPCs, which ones have kind of the endpoints into that VPC. Even things like S3. S3 is a regional service. But that doesn't mean you can't lock it down. What I mean by that is you could create S3 buckets and say that this bucket is only accessible by this VPC, and nobody else could access the data within that bucket. So even if it's at a regional level, that doesn't mean it's not secure within your VPC. You can still lock things down, but it's good to be cognizant. That way you're asking the right questions when you're creating that architecture. So let's dive into the processing phase here. And if we take a look at the processing, the first thing we'll look at is the interactive and batch processing. And really what we'll find here is things like Elasticsearch. Elasticsearch is really fantastic at that log data, the textual data. Redshift and Redshift Spectrum for your really data warehousing needs. Athena, one of my other favorite relatively new services, not that new anymore, where you could actually perform SQL-based querying against your data as it lies on S3. One of the differences between something like Athena and using S3 Select, if you're familiar with that, is Athena is really operating at a logical data set level within the catalog of Glue, rather than doing a selecting of data out of a particular object out of S3. So you could actually have a suite of objects that you're querying over, do complex queries over using something like Athena versus another way of doing different types of gets. S3 Select, really fantastic, but that's one of the differences between Athena and that. And of course, EMR, it's really our Hadoop and Spark ecosystem as a service. Lets you run various platforms, applications. You could actually bootstrap it to run a wide number of tools. It's actually interesting. EMR is one of the services we offer that's really a managed service. You configure how many servers you want. We'll install the Hadoop. If one of the nodes goes down, we'll relaunch it, all that jazz. What's really interesting about it, though, is you actually have root access to the EC2 instances that EMR is using. Most of our managed services, you actually don't have that access. Most of them, like things like RDS, you have a ENI endpoint that you could connect into. You could perform database functions, but you don't necessarily have SSH access into that service. EMR is different, where you actually have, and you actually see the EC2 instances that that service is using and launching and managing on your behalf. When it comes to real-time analytics, really if you're looking at the Hadoop ecosystem, the number of services that do real-time analytics keeps growing. You have Spark Streaming, Flink, things like Storm to be able to run real-time analytics. What's interesting is Kinesis Data Analytics allows you, it's very similar to how Athena lets you query your data objects at rest in S3 using SQL, even though it's not a relational database. Data Analytics lets you perform SQL-based queries on your real-time data, even though it's not really in a database. So it lets you connect, write SQL, things like tumbling windows, random cut forest, different sorts of expressions to be able to analyze that data. It's really easy to write because most people know SQL. But then under the covers, it's going to be processing the data in real time off of your feed and then sending it somewhere else. One thing that I should mention, sometimes I work with customers, and with real-time analytics, it's a very valid question to ask, what's my end-to-end latency from when I publish a message to when I start processing and then get the final insights out? And the tool that you use here that's a really important question to ask as you're picking the tool that you're using. And let me give you a real example. So today, as it stands, AWS Lambda is really fantastic. It lets you write your functions. You can set up an event trigger for Kinesis off of that. But what happens with that is it actually pulls every second off of the event queue. What that means, if your end-to-end latency needs to be less than a second, you really shouldn't be using something like Lambda today because it's pulling every second. It could be more than that. So that's where you'd use something like a KCL or another approach in those examples. So that's why there's these different services, different ways of writing your analytics, different latency requirements for those. And then predictive analytics. There's a lot of sessions and a lot of updated diagrams from the one that you see here that lets you build different types of machine learning algorithms on the platform. And the key thing I wanted to point out here is when you're looking at the architecture of your data system is really just making sure the data is easily consumable using open standards. So it doesn't necessarily matter if you're using Parquet versus RRC for a lot of these systems. As long as it's in an open standard, those are two column-oriented formats. Or if the data is in CSV versus JSON versus different formats. The key is really to have the data in a form that's very easily consumable and used by a lot of these different tools, including the machine learning libraries. The platform, for folks that aren't aware, at the very highest level, we have application services. These are really built to be able to consumed by anyone. They're very, very simple APIs. So if I want to do a transcription of a feed, and I want to get the transcription of that, I could just do an API call, point it to my audio file, and get the transcription out. These are powered by machine learning, deep learning. They're always getting better over time, and it's really, really easy to empower my system with these intelligent capabilities. And there's really a suite of these, and this number is constantly growing. And then at the lower level, we have things like SageMaker. This is really where a lot of the data scientists live, being able to build their own machine learning models, have a managed platform such as the Jupyter environment to build those models, plug into the catalog, and be able to run model endpoints, that sort of thing. So if we take a look at here, you'll notice we kind of color-coded, the real-time data is definitely the fastest. When we're looking at things like Elasticsearch, Athena, Presto, Spark, those are all very, very fast. If you're really looking at things like Hive and Pig, those were some of the original analytical tools out of the ecosystem that got developed. Those tend to be a little bit slower. They're actually under the covers still running kind of old school MapReduce to be able to run those analytics and then write the results out. So here's a couple of slides here. These are going to be on SlideShare, so I'm going to skip over a couple of them. And then talk a little bit about ETL. And then after this slide, we're going to dive into the demonstration. So, why do we want to do ETL? So one of the best practices is really to consume the data as it's coming in the raw form, right? Because if you're transforming the data and there's anything ever wrong, it's really hard to recover from that, along with other reasons. So what we find, and this is a very, very well-established pattern from folks like NASDAQ and Dow Jones and FINRA and lots of customers doing this pattern, but the data is coming in its raw form. What that means is it's coming in, and then oftentimes you want to create curated data sets or canonical data sets that represent a normalized view of that data. And that's where the ETL or the ELT process comes in. And that normalized data set oftentimes is in a different format. So you might have different data sets coming in, one JSON, one CSV, and your output oftentimes will be something like a column-oriented format like Parquet or RC, or if you have constantly changing schemas, you might do something like Avro because it just handles changing those schemas a little bit better. And that's actually the curated data sets that get consumed even farther downstream. So to show that, I think we'll go ahead and actually dive to a demonstration. What we're going to do in this demonstration is show some raw data that we've brought in. And if we could go ahead and switch over, thank you. So what we have here is we actually have the Glue data catalog. And if we take a look here, we're actually going to look at this database. And you can't see me do my air quotes. This isn't a real database. This is really a logical grouping of data sets. And this is in my data catalog. I'll make that bigger since this is a nice big room. So this is actually a logical grouping of data sets that I have that I want to be able to analyze. So if I actually take a look at those data sets here, what you'll notice is some of these data sets are CSV and some of them are Parquet. And this is the first data set we're going to start analyzing. And this came in the raw form. So this came from New York City Taxi Commission. It's 2 gigs of data that we're going to start analyzing. And it's going to work really, really well. It's only 2 gigs of data. We don't need to transform it. It's going to be pretty performant, and we're going to start analyzing it. So to do that, what we could do is we could actually go back over here. And right now we're in the Glue data catalog. And we can actually go over here and say, I want to view the data. And what this is doing is this is shifting to Athena. And you'll notice we're actually issuing select statements as if it's in a relational database, even though it's not. So the data is still at rest on S3. Oops, I might have to zoom out a little bit. The data is still at rest on S3. We can start looking at the data and start querying the data here. And I happen to be using Athena here, but you could actually use Hadoop. You could plug this into the SageMaker and start doing machine learning models. I could start doing a wide number of analytics on this data. This is actually doing just a select limit 10. That's kind of quite frankly pretty boring. You'll notice it only scanned 2 megabytes. That's actually because I actually was limiting the query by doing that limit 10. If I actually do a count here in the average trip distance, this is 1 month of data. You'll notice it's about 140 million records, 14 million records. So we just queried over 14 million records in 4 seconds. Pretty interactive, right? Being able to start looking at this data, analyzing it, see what are the outliers, do some data cleaning, that sort of thing. What gets interesting is instead of 1 month of data, what if I brought the data set in and instead I brought in about 8 years of data instead. So I'm going to actually query that data set next. Oops. Okay. And this is going to take a little bit more time. So we're actually limiting it to 2016 and 15 in the query, you'll notice. But because the data is actually structured here, we just took the raw data, we loaded it in S3. We didn't do much with the data. We just loaded it in, and we're starting to query it. If we take a look at this data, what it has is each file is actually a month of data. Each file is about 2.4 gigs. And what this is doing is this is actually scanning over all this data. It's not using like the file name, doing like a regex underscore and only looking for those years. It's scanning over all the data, finding those 2 years of data, and aggregating those results back to me. And let's see if that was the right timing for stalling. It was. 28 seconds it took to query that data and get the result back. So, it's doable. Like if I needed to do a couple queries and I'm fine waiting 30 seconds. But if this is a system powering data scientists, data engineers, maybe an application, you can't really be responding within 30 seconds here. And this is where we start going through that ETL process. So can we structure the data in a better way so it's much easier and more cost-effective to query this data? You'll notice under the data scanned, it says 207 gigs. What that means is it cost me about $1 to do this query just now to be able to scan over it, because what's happening is it's scanning over the entire data set. And if I would have done really any query here, it's still going to say 207 gigs because it's always scanning over the entire data set. What I could do, though, is I could actually structure the data a lot better. If I actually structured the data so that each prefix on my S3 location was split out by year, you'll notice I'm actually querying it's a very similar query. I'm just querying a slightly different table here. And if I type it in right, if I actually now query this, what's going to happen is it's actually going to do partition elimination. So the way this data is actually stored on S3 now, just to show everyone, is if we actually go back over here now and look at the partition data set and this data, you'll notice that in S3, there's actually a prefix where it says year is equal to 2009, year is equal to 2010. And each of those prefixes or directories, it's object storage, not file system, but directories, when I do that query, I don't need to be cognizant that the data is stored in here. I just do my query saying year is one of these two. And the systems, if it's Athena, if it's Redshift Spectrum, if it's EMR, automatically knows how that data is stored through the catalog and is able to query that data. So over here, you'll notice this took 15 seconds to run now. So about half the time. It scanned 9 gigabytes, so that cost me about 4.5 cents. So same query, before it cost me $1, now it cost me 4.5 cents. What I could also do, though, is if I actually structure the data as Parquet, Parquet is a column-oriented storage. What that means is rather than storing rows of data together, it actually stores column blocks together. And the reason why that's more performant is a lot of these queries aren't actually pulling a single row out for like a database would if it's like a transactional database. What it's doing is it's aggregating over a lot of different data sets. It's doing group bys over different columns, and it's doing a subset of the columns. And by storing it column-oriented, you'll actually notice usually a very, very order of magnitude performance difference here. So if I actually run this query now, you'll actually notice a couple things. It's actually going to return in 4 seconds now. None of this is pre-staged. It's all kind of live hitting US East, you'll notice. It returned in 4 seconds. The other thing you'll notice, same exact data set, just structured differently on S3. It actually scanned over 349 megabytes. So that literally cost me less than about a tenth of a cent to just do. So we just went from $1 to a tenth of a cent just by structuring the data slightly different on S3. And that's why, if we actually switch back to the presentation now, that's actually why we go through this ETL process and create these curated data set. It not only increases the performance for all the analytics, we happen to be using Athena here, to be able to consume that data, but it also decreases our costs and really makes the system more performant overall. And then all those old files that we have out there, if this is a system that was used in production, I could actually archive all those old CSVs to Glacier. I have them if I ever need to rehydrate them, and then all the users would actually be querying that Parquet partition data sets to be able to analyze their data. We have more cool demos, I promise. In 20 minutes, we'll see if I get there. So Here's some of the different trade of which ELT, ETL tool to use in different scenarios. Really, Glue is fantastic if you have data lake requirements, if you're querying external data sources, moving large data sets. We have data pipeline that many of our customers are still using. A lot of questions I get a lot of times is, should I use something like DMS with schema conversion tool, or should I use something like Glue if I have a relational database? And a lot of times that becomes a question on how much data is getting transformed, how much manipulation of the data has to happen, and also over time how you want to populate the destination. So things like Glue are really fantastic. You could take the data set, you could create different fused data sets and store it back to a Redshift or one of those data repositories. But if you need to do CDC, change data capture, things like DMS or one of our partner products is really where those shine. Glue today doesn't actually do something like a change detection. You're issuing queries and you could do your own where clause, but it's not doing the binary logs of the change detection like a lot of the partner products and DMSs. So going a little bit to the consumption model now. I get asked sometimes, what type of BI or what type of UI should I use in this type of solution? And what we find is really depending on what the user is and what function that they want to perform, oftentimes they'll use different tools. So if you tried to put a business user in front of a Jupyter notebook, I'd hate to see what happens there. And likewise, if you actually put a data scientist in front of like some whiz-bang dashboard and didn't give them access to the data, that would actually probably be just as bad. So in these solutions, you'll actually find a suite of different UIs being used to be able to perform these analytics. So Jupyter is used quite a bit within the data science space. There's really two common patterns that we have customers use Jupyter today. SageMaker, which we're going to demo here in a moment, allows you to have a managed Jupyter environment running both Jupyter as well as Jupyter Lab, which we're going to show in a moment. You can also run managed Jupyter or managed notebooks right now on EMR. So if you're really just looking at the Hadoop ecosystem, we actually launched a feature where within EMR, our managed Hadoop platform, you could also run those notebooks. Of course, there's like the Stack and Kibana to be able to do log analysis. We have partner products like Splunk and Tableau and MicroStrategy. And sorry if there's any partners in the room that I missed you, but a wide number of different partner products to be able to perform that capability. So for putting all this together, I know it's an eye chart, but we kind of have this data flow where you have the various data sources flowing in, different repositories based on the requirements that are needed to store that data. One of the key callouts I'll make that wasn't on the previous diagram is that ETL process. How can I take my data, create it in the most consumable method for different types of users to be able to process and analyze that data? And then ultimately getting it to drive insights, to be able to answer business questions, that sort of thing. So we're going to step through some design patterns now. And kind of shifting back to that data temperature. And if we take a look at that data temperature, we actually have real-time data. So over on the left-hand side, things like Kinesis. We have databases, transactional databases, and all the way to data lakes, cold storage, that sort of thing. If we take a look at the streaming versus interactive versus batch, what we have is we actually have streaming analytics done off of a streaming data source. I just like to show this because it's intuitive when you say it, but it's nice. Oftentimes it takes saying it where you have streaming analytics obviously off of a streaming source. You wouldn't necessarily do streaming analytics off of S3 per se. What you have is you could actually have interactive analytics off of a lot of these data sources. If you have a streaming data source and you want to really perform interactive analytics, the most common practice is to actually take the Kinesis stream or take the stream, pipe the data to S3, and then using the suite of different tools that you have available to you to be able to process that data once it hits S3. And we'll talk about a couple customers in a moment that are doing exactly that. And then finally, kind of the batch processing that might be using Hive, it might be using AWS Batch, that sort of technology. So let's step through kind of examples of all these. So data streaming in. Very often you want to be able to run real-time analytics on that data. So you could use Kinesis Data Analytics. You could use the KCL, the Lambda, EMR with Spark streaming, those sorts of things. From there, you might want to be able to run real-time predictions on that data, maybe through like a SageMaker endpoint. SageMaker endpoints allow you to build these models, have an endpoint that these services could call, and then once you actually call that endpoint, if it's outside certain thresholds, you could actually then alert based on certain notifications, send all that data to S3, and then finally create these materialized views or app states. And this is an area where if you have a need to be able to create KPIs, performance indicators, this app state is really one of the core kind of architectural components I see a lot of customers use, where it might be a caching like a Redis or a Memcache, or it might be Dynamo. We'll actually show an example of a customer using DynamoDB with API Gateway with a real-time flow here in a moment. Actually, we'll do that next here. So the first of two examples that we're going to run through, these are real customer examples, is Hearst. They're a media and information company. They have a wide number of different channels. They have magazines, newspapers, things like ESPN, A&E, lots of different channels out there under the Hearst umbrella. And this is actually a real flow that they have. So they have various information coming from their websites going through Kinesis data streams. Once it hits data streams, since it's a stream, you could have multiple consumers, right? One of those consumers could store my data out back into a data lake or a data repository. And then another consumer could actually build a real-time dashboard or build a real-time analysis of that data. And this is exactly what they're doing. So the data is actually flowing to a fire hose, which is storing the data to S3, which then you could really use any of these tools on. And then another consumer is going through a Lambda pipeline, hitting DynamoDB to be able to store that app state or store that analysis state, which is exposed through an API gateway, which allows you to have a RESTful endpoint defined through Swagger to be able to get the current state of that data. Another example that we're going to step through is actually Yieldmo. This is, they have thousands of devices out there, mobile devices, that is getting sent through a data stream. What they're running is data analytics now. So in the first example, through Hearst, they're using Lambda. What that means is their developers wrote function codes, little functions, to be able to process the data, the real-time data, and then store the data into a Dynamo table. In this example, what this customer is doing is actually writing SQL now to be able to run the same sort of processing on the real-time feeds that they have, and then do aggregations, do filtering on that data to then store it out into their data warehouse through a fire hose and an S3 channel there. So I'd just like to show kind of two real examples as we're stepping through these architectures here. Through the batch analytics and interactive analytics, you still might have streaming data coming in. So just because I have clickstream data, I might want to start analyzing the data interactively on what certain users are doing, what different profiles of users are doing, that sort of thing. I also might have other data sources coming in S3 on a wide variety of methods. It might be through Snowball. It might be through S3 accelerated transfer, different data sets coming in at S3. I might want to integrate different data sets from organizations that might be within my company or different companies. We have a lot of data sharing happening on S3 through things like an open data program, a public data set. So there's Landsat data out there, there's genomics data, lots of different data sets being shared through S3 and then analyzed downstream by a wide number of different companies. Obviously, you can completely lock down the data within S3 as well. So as soon as the data is coming in, the streaming data could actually get flows through S3, but also could get loaded into a Redshift or Elasticsearch. But also for the processing, you could use Athena, you could use, which we actually just demonstrated, you could use EMR to be able to do that interactive processing. For the batch processing, we actually see Spark used quite a bit now for batch processing. It actually used to be Hive and Pig, where the predominant language is used a lot of times. We're seeing more and more Spark used for the ETL and the batch processing as well. And that really kind of is tied together through the machine learning. And that is what makes up that interactive layer as well as the batch layer that we see. To show an example here, FINRA. They ingest sometimes about 75 billion events every day. What they're doing is they're actually taking stock information, financial trade information, and what they're really looking at doing is being able to find things like market manipulators or other anomalous behavior on the stock markets. So what they have is they have all this data flowing into S3. They actually have that canonical data issue, so they actually have different brokerage firms reporting data in different formats. It goes in the raw form, it gets into a canonical form, and then they're using a wide number of different EMR clusters as well as Redshift clusters to be able to process this data. And the reason I want to show this is just showing the flexibility of, as you're architecting your solution, storing the data in a format that is easily consumed by not only multiple types of the same service, like multiple EMR clusters, but also consumed by your data warehouse, by your data lake analytics, by your machine learnings, that sort of thing. So if we take a look at the data lake architectures, and there's some really good sessions on data lakes throughout the conference here, so definitely recommend those sessions if you're looking at building a data lake. But really, it's tying in the real-time processing, the interactive and batch processing. You'll notice S3 is really the center of the lake here, but another really important aspect of the data lake is really metadata management. Sometimes when I talk about data lakes to customers, when they ask them, what are you doing for metadata, for the governance, for the provenance, those sorts of things, it's really good to have answers for that. So the data in S3 is a really, really good start, but also having a common data language, a common metadata store, so you can use all these different tools to be able to process your data. So I think next what we'll do is we're actually going to shift over to another demonstration here showing the flexibility of how to use these different tools. We're actually going to be leveraging the same data set that we were just querying. So if we could go ahead and shift over, thank you, to the laptop, what we're going to show here is this data set that we're just querying over. What if I actually wanted to take this data set and do things like extend my data warehouse into this data set, start doing machine learning in this data set to show the flexibility, right? Show the future proofing. I started with a very small use case analyzing the data, but I want to add on top of this. So what we're going to do here is we're actually going to launch into this Redshift cluster. So I have this Redshift cluster currently running here. And what we're going to show here is I'm going to actually connect into the Redshift cluster and show you guys the screen here. So I actually just connected into this cluster, and I'll make it a lot bigger for folks. I happen to be using pSQL here, but really I could be using a BI tool or another type of SQL tool, DB Visualizer, SQL Workbench, that sort of thing. And what you'll notice here in my data warehouse is I have my tables here, but I also have no other schemas defined. So I just have my one table defined here. What I'm going to do here is I'm actually going to define, so this is leveraging Redshift Spectrum now. So at first we were demoing with Athena. Now we're actually doing some stuff with Redshift Spectrum. And I'm actually going to create the schema. And if we actually take a look now, we actually see the schema that we just created. And the nice thing about this now is I could actually query the same data that I was just querying. So if we actually take a look at these data sets, it probably looks familiar. We're just querying the yellow, single yellow partition. I could actually take this data and use my BI tools to start querying this data. Not only that, I could also fuse the data with data that's already in the data warehouse with data that's in the data lake using Redshift Spectrum. Some really good patterns there to be able to start extending that data across the different lakes and the warehouses. But what we could do is, taking that same exact data set, we could also have this EMR cluster. So I actually launched this EMR cluster. I launched it with Hue, Zeppelin. I have different web interfaces into this. So I could use this cluster. I could run my jobs, hit that same data repository. The reason I know that is I could actually go over to the configurations of this cluster. And you'll notice a couple things. One is I actually told it to optimize it for Spark. This is really good to do if you're using EMR and you're just using Spark. Definitely set this configuration. It sets the properties for Spark to use the full memory and the different settings out of Yarn. But you'll also notice it's using the Glue data catalog here for things like Hive and Spark Hive. But what I could do now is I'm actually, instead of running things directly on that cluster, I'm actually going to launch into SageMaker now. And we're going to go into SageMaker. And we're going to go into a Jupyter notebook. And within this notebook, what we're going to do is we're actually going to start querying that same exact data sets that we had. So because it's in an open format, it's in CSV, Parquet, these different formats, I can actually go in here and start analyzing this data. So what I'm going to show here first is within here, I could actually re-execute these cells. I could actually query this data set. You'll notice this is actually the same data catalog, so that metadata management is really, really key on this. How am I cataloging my data? So in here, I could actually query my different data sets. I could actually go in here and start bringing this into a pandas data frame now. So I actually just, through the EMR cluster, through Spark, I queried, earlier I actually queried all of the taxi data, and then through the Livy integration, I actually brought it into a Panda data frame. And over here, I could actually do all types of different Pandas things within the Spark or within the SageMaker environment now, or really the Jupyter environment that SageMaker is providing. Not only that is, if I actually want to build my own model, maybe I want to build an XGBoost model to be able to do a regression or something like that here. What I could do here is through the Jupyter environment, I could actually trigger this, this job to run. You'll notice I'm actually specifying different node types. So definitely, if you're looking at doing machine learning, attend some sessions on SageMaker lets you run these Jupyter environments that have very low footprint and then spin up these training jobs that could be very, very large and auto scale up and down or really scale up based on your definition. So what I just did, though, through that SageMaker Jupyter environment, hitting that Livy server, I actually just triggered this SageMaker job. So if I actually go over to the training jobs now, what we'll see is we actually just triggered this training job all through the integration of the platform. And we happen to be using AWS products now. I could be using other partner products on some of these. I could have actually shown a Tableau or a Jaspersoft MicroStrategy, one of the BI tools in front of the Redshift rather than the P-SQL. So there's a lot of nice integration through the partner ecosystem as well. If we could actually switch back to the presentation. We're going to wrap up here with like 2 minutes to spare. It's kind of how we roll. So just to wrap up, as you're building these systems, building that decoupled architecture, the way I'm ingesting data or the way customers are ingesting data versus storing it versus analyzing it, really good to decouple all those different steps so that you can use these different tools. You can swap out the best tool for the best job. Also, leveraging managed services, serverless options really lets you focus on what matters. And I will highlight the cost-conscious aspect. If you're actually pricing out an architecture and it becomes a very, very large cost, usually the way we price our services are based on the way that service is intended to be used. For example, if I actually try to write out a lot of really small files to S3 and I cost that out, the put costs for S3 actually go very, very, very high, rather than using something like a Firehose or like a DynamoDB, which is meant for that very, very high throughput, low payload write type of architecture. So just go through that pricing exercise. Get involved with your AWS teams to help you with that exercise, and that really helps validate that architecture. So definitely want to thank everyone for their time. Please remember to fill out your reviews, and hope everyone enjoys the rest of the day in the conference.